Okay, so can everybody see the slides?
Yep.
And also the transition is fine, right?
Yeah, it's working.
Great. Yeah, while we're still waiting for more students to join in, I'm just trying to remind everybody to start with homework 2 earlier because we have 14 days to do that. I'm happy to see a few questions have been asked in Piazza, and we're watching the Piazza and trying to help you. And the workload for this homework is much smaller. As long as you have a robust implementation of decision trees, that should be fine. And but you do need some time to run those back in boosting, and also run kind of lengthy experiments to get the estimate of the the bias and the variance decomposition. You need to get some accurate estimation of that, and observe that how the bagged prediction, namely doing an average of a set of independent, not independent, less correlated tree predictions will indeed significantly reduce the variance term, and so that finally you get like smaller square error. Right? That's something please be aware. Is the problem is definitely not hard, but you do need some time to run those experiments. It will take some time. And the second thing is about the cross project choice. So someone asked me, confirm with me. So let me emphasize again. If you choose to do the Kaggle project, competitive project, you are not required to submit one-page document to Canvas, or it's totally optional. If you want to do that, you are more than welcome to do that. But it's not obligatory. But you do need to fill out a Google spreadsheet shared by our TMs, because our TM need to know uh, what is your ID and what is your account name, so that they can track your records and ranking in the Kaggle computation. Okay. So any question regarding these two things, homework 2 and the course project choice? Great. Okay. So let us continue with linear models. So in the last lecture, we have introduced the definition of linear classifiers, right? So basically, we define the prediction function as a sign of a linear classification function, which is a bias term B plus the inner product between a weight vector and the feature vector or input vector, right? So of course, if the classification function is bigger than or equal to 0, their sign is positive, then your prediction is positive, right? Otherwise, if the classification function is negative, your sign is -1, you're going to give a negative prediction, right? So this is the key definition of the linear classifiers. It's pretty straightforward. And in practice, I mean, to make the notation even simpler, right? We usually uh, append, no, not append, actually insert a constant feature 1 into the original input feature vector. So we got our new augmented feature vector x prime. Correspondingly, we insert the bias term B into the weight vector. So we got a new weight vector w prime. Uh, in this way, we can write our classification function directly by the inner product between w prime and x prime. So we do not need to explicitly write out the bias term B. That's the only motivation of using this notation. Nothing special, right? But just to be, but you should be aware that even we write our linear classifier in this way, by default you need to know, okay, there is some kind of hidden constant feature 1 in the input feature vector and bias parameter B in the weight vector. Okay, and then we introduced then we'll talk about the geometry of linear classifiers, right? Let me find the slides. Yeah. So actually, the classification boundary, which partition the whole input space to two half spaces. One space contains all the positive examples predicted by our classifier, and the other are negative examples, right? Those classification boundary is represented by an equality where the classification function is zero, right? So the weight vector can be shown to always perpendicular to the classification boundary, right? We haven't shown why, right? You can verify it as a practice of your high school geometry, and all the points which stay on the side where the vectors, the corresponding vectors, are aligning with the weight vector will be classified as a positive because their vectors, the angle between their vector representation and the weight vector is less than 90 degrees or pi over 2. So it can be showing that the classification function will be positive, otherwise it will be negative. So in a two-dimensional space, this classification boundary is a line. Right? Three-dimensional space, it is a plane. Right? In an arbitrary space, we usually call this boundary as a hyperplane or classification hyperplane. So this geometry is really useful and very intuitive, and we'll continue to review it and use that to explain more advanced linear classifier learning algorithm as like in support vector machines. We'll discuss about later, right? And then we'll talk about how expressive linear classifiers are, right? We use the Bloom functions as an example, right? We have showing that, okay, Bloom functions, linear classifiers are quite expressive, like they can perfectly represent functions of conjunction of Bloom variables or disjunction Bloom variables, or even you insert the negation operators inside these conjunctions, disjunctions, so you can still find a linear classifier which can perfectly separate the positive examples and negative examples represented by this or labeled by this target functions. Right? However, and also Emerson rules, another example. However, that does not mean like linear classifiers are expressive enough to classify all kinds of positive examples, negative examples, even in the Bloom function space, right? So a typical counter example is the parity examples. Like if you distribute the positive examples in this way and negative examples in this way, it can be showing that no matter how you draw the line, namely the classification boundary, you will never be able to separate all the positive examples from negative examples. Such function in the Bloom function space includes the XOR function. XOR is a very common used Bloom function, and I mean used in everywhere, like digit, circuit, design, whatever, right? And what is XOR? So given two Bloom variables, x1 and x2, XOR of x1 and x2 is true if and only if x1 and x2 are different, meaning that either x1 is 1, x2 is 0, or x1 is 0, x2 is 1. So if you write down the four possible examples labeled by this XOR function, they will distribute in this way, definitely distribute in this way, right? And we can show you that they cannot be separated by any linear function. And in general, we can define a parity Bloom function in this way, like x includes an arbitrary number of Bloom variables. F of x is 1 if and only if the number of ones is even, I mean inside x. So this conclusion is formally proven by a pioneer in artificial intelligence. His name is Marvin Minsky. So share a little bit gossip. So many of you might have known that AI has experienced several winters, right? And resurgence, right? Right now it's the third time resurgence. Seems won't last for long, right? That's my pessimistic view a point. But anyway, in the 1970s, Minsky published a book and showing that linear classifiers cannot differentiate XOR function examples. And then this is the direct lead that caused a second, depression of AI development. And in addition to XOR function, XOR is a famous example that not linearly separable. There are many other non-trivial Bloom functions that cannot be linearly separable as well. So we know that so far we have discussed quite a few classifiers, right? Decision trees look pretty straightforward, right, and simple and intuitive. However, decision trees are more expressive than linear classifiers. So this is something we should keep in mind. Right? However, along with the development of machine learning, right, the progress of machine learning, people find that, okay, although those non-linearly separable functions, right, their inputs in the original instance space cannot be separated by, a linear classification boundary. Right? If we can make proper and smart feature transformation or feature mapping in a new feature space, we might still be able to find a linear classifier to perfectly separate positive and negative examples. And how can we do that? Let us look at this particular example, right? So in this particular example, all the positive and negative samples are in a one-dimensional space, namely in this x-axis. So obviously, we can now find any line that can well separate the blue dots and the red pluses, right? So you can try to draw a line here, try to draw a line here, unless you draw a boundary like this. Otherwise, you won't be able to separate all the positive examples from negative examples, right? And what should we do, right? We still want to address this problem in the linear classifier domain. How can we do that? Here comes a smart trick. We want to transform the input. How can we do that? The original point, right? Original point in the original space are represented by scalar x, right? So now I want to append an extra feature, which is simply x squared. So now each point in the original space is now represented by a two-dimensional vector, meaning that we place them in a two-dimensional space. This is called feature mapping or feature transformation. Now let us look at what are the locations of those transformed inputs. Right? So here is the two-dimensional space. So remember now each input now is represented by the original location x and x squared. Right? So obviously, in this two-dimensional space, it's pretty easy to find a classification boundary which perfectly separate all the positive examples from negative examples. Right? So this is just to showcase how the representation of the input changes after feature transformation. Right? In the original one-dimensional space, this particular sample its location is -2, right? It's a one-dimensional space, but in a two-dimensional space, it's -2, 4. Right? So in general, any question?
Is this generally an expensive thing to do to your data because you're adding an entire dimension?
Yeah, that's a very good question. In general, yes, especially if you do want some kind of powerful feature transformation mapping, you need to make this mapping to be very high dimensional, like even in an infinite dimensional space. So I mean, in an infinite dimensional space, meaning that you cannot explicitly do the feature mapping and then calculate everything. You have to find a smart way to get over that. So that will lead to the so-called kernel trick. So basically, this idea will be applied again and again in the machine learning domain, and it will lead to the more general trick, more class of tricks called kernel trick or kernel methods, So actually, machine learning is a very important branch of methods. The idea is to how do we construct a new feature space where by some smart feature transformation, you can map the original inputs into this new feature space. And then you can, in this new feature space, you can apply much simpler classifiers like linear classifiers to do everything. Then the remaining question is that how can we avoid explicit computation of this feature mapping? The most common used trick is called kernel trick. We're gonna cover it when we discuss about support back machines. Okay. So now I will leave this as an exercise for you. It might show up in homework 3, right? So as we just mentioned, right, for XOR function, you're not be able to find a linear classifier which can separate the positive examples, negative examples labeled by XOR, right? So now what if we want to apply this trick, right? Can you come out a feature transformation such that after the mapping, you can still find a linear classifier to perfectly predict the positive and negative examples labeled by XOR. So please think about that. Okay, that's about some like a preliminary introduction about idea. Right? You can view that although the model, the linear model itself, is kind of like simple, right? It's not too complicated, right? And seems not powerful enough to address the complex situations in real world, right? Like nonlinearity and etc. Right? But if we can smartly apply this feature mapping, nonlinear feature transformation trick, we can still apply the simple linear structure to address complex problems. Right? That's actually the key idea of many sophisticated machine learning models, which we're going to discuss later, right? So okay, another thing about linear classifiers. In practice, I mean, even we assume the data are simple enough, right? Pursuing a perfect separating hyperplane is always like over, right? It's too strong assumption. Right? So in most cases, what we're assuming is that, okay, we want the training data is almost linearly separable. Namely, some kind of examples can be misclassified by this linear classifier as long as such examples are few. Right? Like in this case, we know that the positive examples and negative examples are kind of like closing to each other, right? So, but we still can draw a classification boundary, right? Where only two examples are misclassified, right? We will that those two examples are kind of some noisy examples, right? Either their labels are corrupted or their inputs or features are corrupted. Right? Obviously, whether you are gonna view this data set as almost linearly separable or not depends on how much noises do you allow for, right? So actually later when we discuss like general learning, linear classifier learning algorithm like support vector machines, you'll find that we're trying to automatically find a linear classifier for almost linear separable data, right? So then the tolerance level is actually optimized by the algorithm itself. Right? And we're gonna discuss it later, right? So now we have finished the definition and basic introduction of linear classifiers. So to summarize, linear classifiers is an expressive hypothesis class. Many functions are linear or can be perfectly represented by linear classifiers like conjunction, disjunctions, or mixture of conjunction with negations, etc. Right? And it often serves a good guess for hypothesis space. Why? Because in practice, right, no matter when we have a new problem, right, which we believe we only have one solution, and that's machine learning, right, will not build up a 200 layer, 1 million parameterized deep neural nets and buy like 100 GPUs to solve. That's too expensive, right? We always start with kind of simple but expressive hypothesis class, right? If a linear classifier works pretty well or satisfactory for this problem, why should we bother to train a much more complex model? That's why we often use linear classifiers as the initial guess. But of course, we need to realize that the limit of linear classifiers, some functions are not linearly separable, like XOR function, some non-trivial Bloom functions. But in general, we have some trick to make them linear in a higher dimensional representations. So any questions so far regarding the definition, basic concepts of linear classifiers?
Yeah. So to kind of bring it all together as an example, would you say use a linear classifier and say, well, okay, it looks like we're getting some amount of error with the linear classification, right? And then you decide based on the error, that's too much error or that's just fine, right? Like that's good enough. And then if it's too much error, then you might say make them making them linear in a higher dimensional feature space, right? And then classify them again, kind of a thing.
Yes, exactly. Yeah, again, I mean, to say if this classifier is working well or not is totally subject to the user, right? If a user say, okay, on this particular prediction problem, okay, most time as long as you give 90% accuracy, I'm good with that.
Right, and that would be like a hyperparameter, I guess, right?
Um,
Essentially, of like how close should we try to classify?
You can definitely view it as a hyperparameter, but usually we won't set the accuracy level as a hyperparameter. But you can view it as definitely. Like you can use it to choose models, right? You like in front of the desk, you have 5 models. You're gonna use some kind of things or criteria to choose which model you're gonna use, right? Then the accuracy level could be a hyperparameter.
Gotcha. But we're not going towards an algorithm which would, continually assess whether or not it should be expanding things into higher dimensional feature spaces, like based on some metrics.
Continuing expand the feature space.
So I guess what I'm asking is it like, it seems like it would be kind of interesting if a machine would make the decision of whether or not it should expand like the data into higher dimensional feature spaces, right?
Mm-hmm.
And is that something that we'll be looking at, or is that not something that's done in practice?
Well, it's definitely done in the practice, but usually it's not automatic. It depends. The user will first try the simple models like linear classifiers, right? And say if it is good. If it's good, then we just leave it as it is. Right? Otherwise, okay, I'm trying to do some nonlinear feature transformation, and there are a lot of choices of doing this, like different kernels.
Mm-hmm.
Yeah, but yeah, this procedure is indeed widely present in the practice, right? But it's really is not like an automatic procedure to do this.
Can this mapping to a higher dimensional feature space result in overfitting?
Yes. Yes.
So how do we then separate out that we need these features and not like
so you can see that this is actually not directly related to overfitting.
Okay.
Yeah, because you are not increasing the parameters. So you see the simple examples I give there, you just appending an actual feature x squared. You're reusing the information in the input. You're not trying to add 1 million more parameters, although you can do that if you like.
Wouldn't doing that make it more sensitive to noise though, and therefore like
yeah
and then it would be like overfitting? Yeah,
it is possible. I mean, yeah, if you add more parameters to make your model more complex, yeah, of course it might be more sensitive to the noises. Yeah, but there are other ways to control that, like if you use different learning principle, like maximize the margin of linear classifiers with respect to the data, you can effectively, innovate such kind of sensitivity. This is what we're gonna talk about that. But right now, when we talk about the feature transformation or feature mapping, we're trying to address another problem, which is at another extreme where you underfit data. Right? because you cannot, because with in our original feature space, you cannot use linear classifier to wall fit to the trained data. I'm trying to using some tricks to make the model more flexible to better fit the trained data. But of course, if you make a model, if you increase the model complexity, like you introduce more and more parameters in your feature mapping, you're increasing the model complexity as well, right? Then you move to another extreme, like your model might be too flexible, too expressive that you're so sensitive to noises and lead to overfitting. Does it make sense? So you see what I'm saying? Like the feature mapping and feature transformation is trying to address the underfitting problem. Yeah, of course. What you're concerned about is about overfitting problem. It's on the other side, right? Okay. Yeah. So last thing we need to be aware, like why do we need a bias term? Right. We see that when we define the classification function, right, it is inner product between the weight vector and the input feature, then plus bias term. So why not we just remove this bias term? Then we can write W transpose X. That's it. Why can't we do that? Any idea?
Distance, for the distance between like trying to make sure that the distance between negative and positive is at least 1, because we can divide the whole thing by b, so the distance is, I'm not sure. So this is,
I think you're cutting the point.
Is it because the data might necessarily be aligned like about the origin, so you have to move the hyperplane?
Yes. You hit the point, right? So if let us imagine that we just get off kick off the speed, right? Well, what will happen? Then if you kick off the speed, then your classification boundary will always pass through this origin, right? So B gives us the flexibility to move to the left, to the right, to the top, to the bottom, right? If you don't have B, the bias term, your classification function, then your boundary always pass through the origin, right? So those weight vector can only control the rotation flexibility. Right? We can rotate them in arbitrary angle by choosing different weight vector, right? But what if we have a set of like positive examples surrounding the origin, right? And then without B, no matter how you rotate your classifier, you rotate your hyperplane, you're gonna always misclassify part of it. So if we have a B, right, we can safely move them to a better place. So that's why that's how B works, right? From the geometry point of view, right? It can make the linear classifier more expressive. Okay, any question? Okay, great. This is just to let everybody know that this B is not something we could ignore. It's actually plays an important role as well. Okay. We have finished the introduction of the linear classifiers. So now we're gonna move to the detailed learning algorithm. So let me share with the let me share with the new slides. So can everybody see the slides?
Mm-hmm.
Okay. So is the transition okay as well, right?
Yeah.
Okay, great. So now let us talk about the detailed learning algorithm for those linear models. We're gonna start from linear regression because we only have one algorithm one learning algorithm for linear regression is called least mean square regression. But we have quite a few learning algorithms for linear classifiers. So here's our plan to introduce the least square method for regression. We're gonna start with some concrete linear regression task. Based upon that, we'll introduce the objective for which we optimize and estimate the model parameters. Then we introduce the two dominant, very widely used optimization methods in machine learning. One is called gradient descent, the other is called stochastic gradient descent. Okay, so here's our task. Suppose we want to predict the mileage of a car from its weight and age. Suppose you're a dealer or car rental company, right? So you can weigh in actual car and you can know the age of the car, and now you want some automatic way to predict the mileage. Suppose the odometer is broken, right? So here are the samples of those cars and our mileages. Each row corresponds to the weight, years, and the mileage rate, right? So from those examples, right, we want to learn a function that can predict the mileage using x1, x2. So x1, x2 are weight and age respectively. This is our task. So obviously, this is a regression task. Why? The output is a continuous number, right? And what is linear regression? As the name suggested, we're going to predict continuous values using a linear model. So how do we define the model, right? We assume the output, the continuous output, is a linear function of the input features. In our case, we have two features, the weight and age. So we assume the mileage is some Bios term, W0. Now we use W0 just for convenience, plus W1 times X1 plus W2 times X2. So you can see we have exactly the same function form for the classification function in a linear classifiers. Right? But now we do not take sign because our output is continuous value. We do not need to look at the sign, we just look at output value. Right? So this is our key assumption about linear regression model, right? And our learning is to use the training data to find the best possible value of those parameters, including the bias and the feature weights. So once we have identified these parameters, the weight vector W, we can use them to predict the mileage for some new test cars, right? Even as long as we're given their values x1, x2. So this is the whole strategy. And for convenience, right, we're gonna collectively represent all the weights and as well as the parameters back to W. So here we're gonna give a more formal definition about linear regression. So assume our inputs are represented by a d-dimensional vector, and outputs are real numbers. Of course, it belongs to real space, right? So remember, in our model, in our model assumption, we always introduce some Bias parameter b, right? But here we represent W0, right? But for consistency, we can assume this bias term has already been incorporated into the inputs. So our first feature is always 1. Just like the notation simplification trick in the linear classifiers. We assume x1 is always 1. Then the actual features are in the following from x2 to xd. So we actually have a d minus 1 features, right? But we augment the features with a constant feature 1 in the front. So we have our final d-dimensional input vector. And then we assume the output is a linear function of the input features, which is W1 plus W2 x2 plus blah, 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 WD xd, which can be further represented as inner product between the weight vector and the input feature vector x. remember x1 is 1. That's why we just have W1 here. Okay, so this is the whole formulation. Any questions so far?
Yeah. So where does the y come in? The outputs? Oh, outputs are the labels. I see.
Yeah, the output
Creating
label.
labels.
But here we have continuous labels.
Gotcha. Okay, I was interpreting that incorrectly.
Okay. Any other question regarding the formulation of linear regression? Okay, it looks like everybody is on the same page, right? We're satisfactory. So now let's proceed, right? So to give a concrete example, right? Suppose our original features are just one-dimensional, right? So meaning that our x2, right? x2 is just one-dimensional. So output y, we can represent all the points in this plane, right? So here, blue dots represent the training examples. Our goal is to find a line, right, which can predict the output given arbitrary x2, right? So this is our assumption of our prediction function, which is w1 plus w2 x2, right? Again, because x1 is assumed to be 1, right? So here is w1 times 1 plus w2 x2. And similarly, when we consider like two-dimensional inputs, then our prediction function actually represents plane, right? The three-dimensional space. Here is x2, x3. Those red dots represent the training set, and the y-axis is the prediction. So now, suppose we're given a training set, right? We have a set of M training examples, x1, y1, x2, y2, to xm, ym, right? How do we know which weight vector is the best one for this training set? How can we do that? This is the case for the training procedure, right? But as we mentioned before, right, training in general is viewed as a searching procedure, right? We're going to use this training data set to search the best parameter vector, right? Namely the weight vector here. So how can we do that? We're going to define some cost function. So we assume that, okay, we use our model to make a prediction for each training example, say xi, yi, right? We want to evaluate what is the cost for the mistake of our prediction. So a natural definition of the cost is just the absolute difference between the ground truth output and your prediction. That's it, right? So this is your prediction, right? So the larger the difference, the more cost you should pay for that. And the closer the difference, right? The closer your prediction to the ground truth output, the smaller cost you make it, right? If your prediction exactly the same as the output, you don't have to pay any you don't have to pay any cost because you didn't make any mistake. So now our goal is to find out a weight vector using which to predict the training examples, the total cost is the smallest. Based on this idea, we can write down our cost function or the objective function we want to minimize. So here is our cost function. Sometimes it's also called loss function. So it's a function of the weight vector, which is half of the summation of the square error in using our model predicting each training example. Yi is subtracted by W transpose xi to the square. Any questions so far? Okay. So
Yeah, one question. So the 1/2 there, how many attributes or how many features or how many weights, I guess, are in this? Is this an arbitrary number of weights?
there's an arbitrary number of weights.
Okay.
Yeah, it's just the representative general weight. Of course, you can expand it as like W1 times xi1 plus W2 times xi2, blah, 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 right? But here for convenience, we just write it as inner product between, arbitrary number of the features and the corresponding weak vector.
Gotcha. Okay.
Yeah, that's why I said that in machine learning world, like for convenience, people always write everything in terms of vectors, matrices. You don't need to worry about those details, like how many numbers of features do you choose? Right? And yeah, also you mentioned that half, right? Why should we have half? Can we just wipe out half? Yeah, you can definitely, because you can multiply with this objective function with arbitrary positive constant. Right? It doesn't affect the optimum, right? But we will see that by using half, we can achieve a little bit of convenience when we derive the gradient.
Gotcha. That is something I was wondering. Thank you.
Yeah. Okay. So, but the goal is here, right? We define such a cost function or loss function. Right? Our goal is to minimize this cost function with respect to W. Right? We want to find the W by using this W to make prediction. Our cost of making mistakes is minimal. This is our goal. Yeah, our strategy for learning, find the W with the least cost of this data. Right? So you see that many machine learning models, people always ask, okay, what is the loss function for that? So they define the loss function or the cost function in the same kind of logic, but they might choose other definition of cost. But here we choose this widely used square error as a cost.
So the squared error, it seems like, because since it is squared, you get the absolute value kind of effect, right? But you also get like much larger values for bigger mistakes, right? So like if you make a mistake that's very far off, you're gonna get, well, you know, a squared kind of error on that. Doesn't that mean that like if there's outliers, they'll drag the whole plane a lot?
Yeah, that's a very good point. I'm glad you point out at the first glance of that. Yeah, this is a problem of square loss. That's something have been criticized for a long time. Well, I see that choosing the square loss is just for convenience. You see that when we derive the gradient. But yeah, you're right. If you make a wrong prediction, you make a very wrong prediction, that kind of cost will be amplified because you're going to take the square of that. That means the training is more dominated by those hard to classify examples, hard to predict examples. That's some problem with that. To address the problem, people also propose other loss functions, like you can directly try to minimize this absolute value of the difference. The absolute value of error, the issue is that it does not have a valid gradient. You have to come up other way to optimize the weak vector, or you can take some kind of other, the power of this absolute value to alleviate that issue. But here, let us just focus on the square loss because this is the most fundamental and most widely used loss function.
I have another question about kind of big picture with this. So this is no longer, I guess, we're not thinking this in terms of like a linear classifier, meaning that like we're splitting the data. In this case, we're literally just we're basically finding a trend line that represents our examples, and so that we can just use that as predictive.
Yes.
Okay.
Yeah, that's the regression task.
Right. Okay. Thanks.
Okay, great. Yeah, let us continue, right? So now our task becomes an optimization problem, right? We have come out our loss function, also the objective function. Our goal is to minimize this objective function to find the optimal weak vector. But how can we do that? There are different ways of optimizing this, but we're going to focus on very widely used and dominant technologies called gradient descent. Maybe many of you have experience on that. Let us just be patient, right? We need to go through it. It's very important, fundamental. Right? So what is gradient descent? As the name suggests, we're going to use the direction of gradient to move toward the minimum of our objective function. So this is our objective function. Let's just assume we are trying to minimize a general objective function g of w. So here is the framework, right? We start with some initial guess of the parameter vector w, right? We denote it by w0. Then we iterate the following procedures until convergence or the maximum number of steps are done, right? So in each iteration, we're going to compute the gradient of objective at current weight vector, denoted by wt. Then we update wt to get wt plus 1 by taking a step in the opposite direction of the gradient. The intuition is as follows. Why should we take the opposite direction of the gradient? Because the gradient indicates the direction to increase the function. But our goal is to minimize the function. Right? So that's why we need to go in the opposite direction. Let's see some concrete example, right? Suppose this is our objective function. And this is our W0. Now we calculate the gradient, right? And we know that the gradient is the slope of the target function curve at this input W0, right? So now I want to ask which direction is the gradient direction.
It would be up and to the right.
Why?
Because at that point, the gradient is positive, and so we'd be increasing in cost. And so we want to minimize cost, so we should go the other direction.
Yes, exactly right. Remember, the gradient is the slope of the tangent line, right? So from the slope, we can see that the slope is positive, right? So the gradient is positive. And remember, this is just scalar. Input is scalar, so the gradient is a scalar. So it's positive scalar, that means the gradient direction is along this line. If you're along this line, you're actually increasing function. You can see that if you're going along this positive right to W0, you're increasing function. Because our goal is to decrease the function, we need to move toward the opposite direction. So that's where we move W0 to W1, right? And we see that when we move in the opposite direction, we're decreasing the function. And again, we calculate the gradient. Again, the gradient is positive because the slope is positive. So we need to move in the opposite direction. That means to the left, so we get W2, right? And we continue of doing so until we reach this minimum of the objective function.
So W is a vector. How are we taking these steps?
W is vector, but in the vector space, you can still take the step, right? You can add a vector by another vector to move, right?
Right. Okay. And I guess our slope, like the gradient that we get, is going to be a vector. So then we like negate that or something.
Yeah. In a high dimensional space, of course, I can now say, okay, the slope is big, is positive or negative. Here,
Right.
just in this one dimensional space.
Gotcha. So the gradient's a vector, and then like we know we can say that the direction of the gradient is, however it's facing, right? And then we can kind of like reverse that somehow and take a step that way.
Yes, exactly. That's how the gradient descent is performed. Okay, so basically we keep moving our wave vector along this line, the opposite direction to the gradient, right? And until we find some minimum of the objective function. So now let us look at the framework, right? The general framework for our particular least mean square objective function here, right? So we initialize our wave vector denoted by W0. Then we go through many iterations. Inside each iteration t, we're going to compute the gradient of the objective at the current weight vector wt, right? We denoted by like nabla g, right? And then we update our weight vector this way. That's where we just mentioned, right? How do we update the weight vector toward the opposite direction of weight vector, opposite direction of gradient, right? So if we take opposite direction, we need to take minus sign in front of it. Right? And then we need to determine how far away you move along with the opposite gradient direction. Right? This is controlled by this scalar r, and r is also called learning rate. So let me emphasize again, right? Because we're performing gradient descent, so we need to move toward the opposite direction of the gradient vector. That's why we should take minus sign in front of this gradient, and then we multiply with this direction by a step size or learning rate r to finish our update to get w plus 1. And then we go to the next iteration, calculate the gradient accordingly, and update the weight vector accordingly, and so on and so forth. So now let's just assume r is a small constant. Actually, you can show that when r is small enough, you can always find a minimum of the objective function. Does it make sense? Any questions so far? Okay, looks like everybody is comfortable, right? Okay, then the remaining thing is how do we obtain a gradient, right? How do we calculate the gradient? This is the key question we need to address for our least mean square regression problem. So now let us try to derive ourselves. And using experience, we did our practice in homework 0. Hopefully everybody did not forget how to calculate gradient. Right? So in general, because we have multiple features, meaning that we have a gradient vector. Right? So your gradient vector rather a simple scalar. Right? So suppose you have d features, you're gonna have d weights. Right? So then our gradient is a vector of d elements. So we need to calculate the partial derivative of the objective with respect to each weight element. Remember, w is vector with d elements. So now to derive this gradient vector, we're going to start with some particular element, right? By doing the gradient calculation for this particular element. We want to summarize a general formula. We just apply it to every element we can get the whole gradient vector. That's our strategy. So now let us look at how can we do that. Right? Suppose we pick up a particular weight, wg, right? We want to calculate the partial derivative of our quadratic objective with respect to wg. Then we just apply it. Right? So this is our objective. It's a half times the summation, right? So of course we can move the partial derivative inside the summation, right? So we take the gradient of each square error, right? And here we can use the chain rule, right? So we can view this error, I mean, yi subtracted by the prediction as a whole, right? We first take the gradient of this term square, right? And then apply the chain rule. And this is pretty straightforward. You just move the power in front of it and subtract it by 1. The power should be subtracted by 1. You get 2, and this error, yi is subtracted by w transpose xi. Then you apply chain rule, you take the gradient of this difference, right? And now we need to write out this inner product because we only take the partial derivative of this difference, right? We need to look at which terms include wj. Those are only related to wj. All the other terms are will constant. Their partial derivative is simply 0. So see that this w transpose xi is simply w1 times xi1, right? The first feature in the ith instance, w2 xi2 until wj xig, right? The j's feature in ith instance multiplying with the j's weight, wg. We find that there's only one term, this product term, relates to wg. Right? All the other terms are constant to wg, so you can just ignore them and then take the gradient for this product term only. Then we get our result, which is minus xig, right? Because it's minus wj xig. Right? If we take out If you take gradient, just minus xij. So now we can see the benefit of the half here. Right? So we see that when we use chain rule, right, when we take the gradient of this projected term, we have a term 2 in front of this parentheses, right? So now it cancels with the half factor in front. Right? So now we can remove them, and we get our final results, which is a minus summation, the difference between the ground truth and their prediction times the gist feature in each instance. That is the gradient of the objective with respect to a particular weight element. Any questions so far?
What's the xij again?
Xij is the G feature in ith instance. So xi represents the feature vector for instance I or example I. And xij is just the J element in xi.
Huh. Okay. And j isn't in our final equation. J isn't changing, right? Like
No, it doesn't change because we're trying to calculate the gradient with respect to W2, with respect to J's element in weight vector. It doesn't change. So you can see that, okay, you're going to just look at, okay, what is the error in predicting each of these M training examples, and then you multiply each error with the J's feature in the instance. Does it make sense?
I think so.
Yeah. So then we can say we now have summarized the formula to calculate the gradient for one element, right? And of course, we just change the J, right? We can calculate the gradient with WG plus 1, WG plus 2 up to WD, right? So we actually summarize the formula, the general formula to calculate the gradient of each weight element. And also we found this very interesting. It has a very interesting structure, right? It's a summation, negative summation of the prediction error multiplying with the corresponding input feature. Remember, each weight element corresponds to one particular feature. Like W1 corresponds to the first feature. In all the instances, W2 corresponds to the second feature. In all the instances, to WD, right? And then their gradient, they all share the same error, right? Using the whole model to predict every training example, they share the error. The difference in how do they apply this error, right? Which feature they're going to use to apply, to multiply with the error. Okay, so any questions so far? Okay, I have to suggest everybody like try to rederive it by yourself, right? Because I just show all the details, but I don't want you guys just copy and paste. Right? And after all, you're gonna implement this gradient descent algorithm by yourself. It's better for you to rederive this gradient form by yourself, and so you can have better understanding of the structure in calculating the gradients.
I have a quick question.
Uh-huh.
So did they just define the cost function then with this 1/2 out front just for convenience? Because then when we calculate the gradient, we end up not having some coefficient.
Yes, exactly.
Okay.
That's the only reason.
Okay.
I mean, of course, you can throw out this half, and then you have to preserve this 2 in front of it.
Right. And so they're just I guess in a way to like normalize it. That's why we've defined it that way.
Yeah.
Okay.
Exactly.
Sounds good. Thanks.
Yeah. But anyway, if you don't put half and you put other scalar factors, this won't change the optimum of the objective function. It's just for convenience. Okay. Now we can fill out all the details of our gradient descent algorithm for this mean square regression. Right? So again, we're going to initialize our weight vector with W0, and then we'll go through each iterations inside each iteration will compute the gradient of our objective at current weight vector, where the weight, the gradient of each element is calculated following this formula. And this is just to calculate one element. But in your implementation, I highly suggest you to arrange them into matrix and vector calculation, and so that it can accelerate your the speed. And then after we get the gradient, we update the weight vector toward the negative direction or opposite direction along with opposite direction to the gradient, and then multiplying with a small learning rate R or step size. And then we proceed to the next iteration and we compute the gradient again at WT plus 1, and following the same formula, and update the weight vector toward the opposite direction of the gradient until the total error is below some threshold pre-specified, or some maximum number of steps have been finished. That's the whole algorithm. So any questions so far? Okay, so those algorithm steps look pretty clear to everybody, right? Great. Yeah. So someone asked how can we guarantee this algorithm can give you some minimum, right? So here are some theoretical guarantee, although we're not going to cover the details because these are fundamental theorem in optimization. But what I can say is that as long as you choose small enough R, the algorithm is guaranteed to converge to a minimum of the objective function J. Our least mean square regression task, because our objective function is convex, then any minimum is a global minimum. Meaning that as long as you find a minimum of J, you'll find the global minimum of J. That's a very good property. So now this is the whole thing about gradient descent, right? So now let us look at what is the problem for gradient descent. So we see that to perform one single update, to calculate the gradient, right? We need to calculate full gradient. If we want to calculate full gradient, we have to go through all the training examples, right? And collect the prediction error under the current model, multiplying those errors with the corresponding feature values, add them together to get the gradient value. Now, what is the issue here? Any expected complaint?
It will be slow.
Yes. It will be very slow, right? Like if you only have like 100 examples or even 1,000 examples, that might not be a big deal, right? You just calculate it's very fast. But imagine in real world applications, right? It's often the case that you have to process like 1 million training examples or even 1 billion training examples. So even you train a simple linear model, right? To perform one single update, you have to go through 1 million or even 1 billion training examples to calculate all those prediction errors, multiplying with the feature value together to get one update. It is very, very slow.
Sorry, one more question.
Uh-huh.
So despite and I think you were getting at this earlier, so despite all these downsides to maybe the way this is set up, the benefit we get is this guarantee you're showing that essentially because of this, we know we're always going to converge given that R is small enough. But this now means that we're always going to find a global minimum, and we're going to be able to find a solution. And so maybe we could develop a different cost function that's maybe generalizes better, but or like for whatever reason performs better. But in this case, this is like a simple way to be able to get that guarantee, even though it's not maybe the best solution.
Yes.
Okay.
Yes, exactly. Right. That's the benefit. If it doesn't have any advantage, why should we introduce that? Of course, yeah, it does have certain benefit, but I want to talk about another. The problem in another aspect, that is they're too slow, especially in a large scale application scenario. Like imagine that, okay, I have to wait for 1 hour to get one update of the model.
Right.
That's very bad experience, right?
Okay.
In a wider application scenario, people often do not want to wait until your learning algorithm fully converges. Instead, like you want the model to update like enough times so that your model is good enough for practice. That's it. We don't expect that, okay, your model has a rightly arrived at local minimum or even global minimum. That's not necessary. Instead, we want, okay, by going through half an hour, okay, the model has been updated like 1,000 times or even 10,000 times. Okay, it's good enough. Let us use it, apply it. Those kind of requirements are everywhere, like in online, especially like online applications like Facebook, when they update to their friend suggestion or news feed, whatever. They want fast, right? They want fast and give you good quality results. They want like run 3 days and then give you a new piece of news. And that's insane, right? That's the user won't buy it.
Right. I see.
Right. So yeah. So that's so how can we address this problem, right? I mean, gradient descent is definitely a good thing, right? But sometimes it just doesn't satisfy our need, right? How can we address this problem? So here's the solution. So this is enlightened from the computational procedure. So we found out the standard gradient descent, right? To perform a single update, we have to calculate full gradient. And what is full gradient? You need to go through every training example and calculate the prediction error here, and multiplying the feature value and give it to the and accumulate them together to calculate the full gradient, right? And then a natural idea is, why not we just say some example, then we make prediction, and then we just multiply the feature value and use that to update the weight elements. That's it. So you imagine that, suppose I have gone through 10 examples, right? For each example, I say this example, I calculate the error, I multiply with the feature value, I update the weight vector. So after I have saying 10 features, 10 examples, I'll update the model for 10 times. So this is a very natural but very naive approach, seemingly. So such kind of approach is called stochastic gradient descent. So here's the stochastic gradient descent. We just repeat for each example. Like we're not gonna repeat for whole data set. We repeat for each example. We just look at those examples one by one. Right? We pretend that at each step, the current example I am saying is the entire training set. And just calculate the gradient. The gradient is very easy to calculate because I just calculate the error, like prediction error here, and multiply with the feature value. I got a gradient, right? And then I use this example to calculate gradient, and I use this inaccurate gradient to update the model. That's the whole idea of the stochastic gradient descent. So the biggest difference is that, different from batch gradient descent. The batch gradient descent makes one update for every pass over the data. But stochastic gradient descent can be so efficient that it makes one update after processing each training example. So suppose like you have a 1 million training examples, right? To go through the entire training set, after going through the entire training set, batch gradient descent only performs one update. But if you use stochastic gradient descent, it can perform 1 million updates. In this sense, the updating efficiency for stochastic gradient descent is much, much higher, right? So, but someone may ask, right, if this, whether these updates are correct, right? And there are some kind of guarantee, right? We're going to discuss later, right? Actually, the gradient calculated from a single example can be viewed as the unbiased estimate of the true gradient, meaning that although you update your model parameters with stochastic gradient, which is quite noisy, quite inaccurate, on average, the update is still correct. The gain is that in many applications, especially for big data applications, we would rather require more frequent yet inaccurate updates other than very accurate but very slow update. Does it make sense? Any questions so far? Okay, seems a straightforward extension, right? So now let us look at the algorithm details of the stochastic gradient descent. Hopefully everybody will be crystal clear about that because you're going to implement your own stochastic gradient descent for least mean square regression. So again, we're going to initialize the weight vector and then go through many iterations. But inside each iteration, we look through each training example xi, yi. Once we get xi, yi, we make the prediction, we calculate the stochastic gradient, use that to update the weight vector immediately. So here we still apply a gradient descent, but here, because the gradient contains a minus sign, we subtract the gradient. So minus minus becomes positive. That's where we just write as the final result as a plus sign here. And then after we process one training example, we finish one update. Then we look at next training example, and we calculate the stochastic gradient, update the weight vector again until we finish processing all the training examples in the data set. Then we'll move to the next iteration. We continue this until our training error is below some threshold or some other stopping criterion is met. This update rule is also called visual off rule in the neural network literature. Okay, so now, any questions so far regarding the algorithm details about stochastic gradient descent? No question? Okay, yeah, I'm happy to see that. Yeah, implementation of stochastic gradient descent is really straightforward, right? And someone might concern like theoretical guarantees. I can share with you some theories. As long as you choose R to be enough small, and you have to set a proper schedule of that, then with probability 1, or in other words, almost surely, the stochastic gradient descent will converge to some attraction basin, which is a jargon from optimization literature. But basically says with probability 1, you're gonna converge to some local minimum or station point. Okay. So when should we apply stochastic gradient descent? As we just mentioned, when the training set is very, very large. In that kind of applications, right? Even waiting, applying the standard batch gradient descent, even waiting for a single update is too long. That doesn't satisfy our application. We would rather frequently update our model with kind of like a, not very good update. But as long as we update them frequently enough, we can still expect our model can achieve can get close to optimum much faster than the batch version. That's the benefit of the stochastic gradient descent. Okay, so finally, I want to say a few words about learning rates and the convergence spectrum. So, in the stochastic gradient descent literature, if you want to show that your stochastic updates finally lead to a convergence at probability 1, you have to schedule the learning rate to be monotonically decreasing along the number of steps, the number of updates. And there are quite a few different schedules. You can make it convert decreasing to 0 with exponential speed or polynomial speed, etc. Anyway, you have to make this learning rate to be monotonically decreasing. So the learning rate in many literature is also called step size. And although in our homework, we'll provide you some range of learning rate to let you manually tune them and to check out the performance. And in that way, you can have a more sense how the learning rate can affect the behavior, the convergence speed, and so on. But in modern machine learning applications, people have developed a variety of automatic adjusting algorithms. They can adjust the step size automatically for you. You don't need to. You actually don't need to worry too much about the step size. Like the most popular stochastic gradient descent algorithm in neural network is called ADAPT. It's totally the step size is just adjusted automatically. What you need to do is just to feed them an initial step size, which is usually chosen to be like 10 to minus 3 or 10 to minus 4. So, and from the algorithm framework that we have discussed so far, gradient descent, stochastic gradient descent, we can see that choosing a better starting point can also have an impact. Right? Imagine that this is your target function, right? And if you're starting from here, of course you're gonna converge faster than you're starting from here, right? So sometimes in some applications, you need some trick to guess a good starting point. So finally, gradient descent and its stochastic version are very simple. Yet, almost all the algorithms we'll learn in this class can be traced back to gradient descent in some kind of form, including the perceptron algorithm we're going to discuss next. You see that, I mean, when we summarize that, we can still come out an objective function where the perceptron is actually performing some kind of gradient descent. Okay, now we have finished the introduction of linear regression and the specific learning algorithm, least mean square error regression. Hopefully everybody is clear about that and then feel comfortable to implement the learning approach, right? And to summarize, linear regression uses a linear function to predict a real value output. That is a regression task. Regression always predict continuous output or real value output, right? The key assumption of linear regression is the underlying prediction function, which is linear to the features. And our learning principle is to minimize some kind of cost. And in our class, we talk about the square error, right? Summation of square error as the cost. We discuss about its advantages, disadvantages, but it is still widely used, although it kind of amplify large prediction errors. And finally, I want to see that although we introduced the stochastic gradient descent and gradient descent to optimize the objective function, right? For this particular least mean square objective, we can solve it manually. We can derive the optimum by ourselves. Right? So here I leave it as an exercise for you. So here is some kind of detail. You can rewrite the quadratic function in terms of matrix and vector product. And then if you want to minimize this objective, you're gonna take the gradient of this quadratic objective and set a gradient to be 0. You see that the optimal solution of the width vector has this following form. So please use your pen to derive this after the class. Okay, thanks everybody. See you on next Tuesday.